Okay, so now we're ready to start our area calculation. So we want the area between the graphs of the functions sine of x and cosine of 2x, right? These were the two functions, and we want them between 0 and pi over 2. So let's just start by using this formula here. We'll take the definite integral from 0 to pi over 2, and then we'll take, we can go sine of x minus cosine of 2x, or you could go cos of 2x minus sine of x. You don't even have to worry about which function is the upper function and which function is the lower function, as long as you add in these absolute value signs, right? So technically this can't be wrong right now, although there's still plenty of work to calculate it. So the first step is to remember that we determined there is a point of intersection at pi over 6. So we're actually going to split this up using properties of the definite integral. We can write this as the sum of two definite integrals. One that goes from 0 to pi over 6. And then again, we'll still have the absolute value of sine of x minus cosine of 2x. And then we're going to add to that the definite integral going from pi over 6 to pi over 2. I'll just fix this a bit so it goes up. So that's the definite integral from pi over 6 to pi over 2 of the same integrand. It's the absolute value of sine of x minus cosine of 2x. Okay, let's call this A1 and call this A2. And then we can just calculate them separately. So here's how we'll start. We'll start by working out A1. Well, let's just write it out what its definition is first. It's just the definite integral from 0 to pi over 6. This is a bit repetitive here. That's okay to repeat this, but this is going to be the definite integral from 0 to pi over 6 of the absolute value of sine of x minus cosine of 2x. So now we're going to actually look at how do you evaluate this. Well, if we had the graph, we could just look and figure out which function is on top, the sine of x function or the cosine of 2x function, and then rearrange this so that it was just the top function minus the bottom function, and we could throw the absolute value signs away and be done with them, and then we could proceed just like we did with previous examples. But we don't have a graph available. Now, and if you have a graphing calculator right beside you, resist the urge to look at it for now. Let's just do this by hand. What do you know? You know that between 0 and pi over 6, either sine of x is on top for that entire interval, or cosine of x is on top for that entire interval. Now we also know that right at pi over 6, the two functions intersect. So technically neither one's on top right at the point pi over 6, but at every other point in the interval 0 to pi over 6, exactly one of these functions is on top, and it's going to be the same for that entire interval. So why don't we just take one point in the interval 0 to pi over 6 and test both sine of x and cosine of 2x and see which one's on top. Now the only point that won't work as a suitable test point here is actually pi over 6 itself, because that was the place where they were equal. So we know they're both going to be equal at pi over 6. Well, what's the next easiest point to plug in? I mean, you could pick any point between pi over 6 and 0, but there's a lot of points in between pi over 6 and 0 that would be really awkward to plug into sine and cosine of 2x. So how about we just plug in 0? That's a perfectly reasonable point. If we plug in 0 to sine, well, you get 0. If we plug in 0 to cos of 2x, you get cos of 2 times 0, which is just cos of 0, which is, of course, 1. So that means cosine of 2x is greater than sine of x at the point 0. Right, because 1 is greater than 0. But because of the fact that it's going to be the same, one of the functions is the top function for that entire region. That much you know at this point. So if cosine of 2x is the greater function at the point 0, it's got to be the greater function for the whole region. So what you can do now is just rewrite this so it doesn't have the absolute value sign anymore. You can just write this as 0 to pi over 6, and you can just write this as cosine of 2x minus sine of x. Right? Another way to think about it is this. If cosine of 2x is the top function, then sine of x minus cosine of 2x is actually going to be negative. All the stuff inside these absolute value signs is actually negative, which means the absolute value sign is going to have the effect of introducing another negative sign, which changes the order of subtraction. And that's why the absolute value signs here effectively just change the order of subtraction. And now we don't have to worry about the absolute value. Now we can actually proceed and calculate this definite integral. And let me just put a box around this so it doesn't get confused with the main thread of calculations. This was just side work to figure out which of these two functions belongs as the upper function, but now we can carry on with our calculations here. So let's find an antiderivative for cosine of 2x. You can do a substitution here if you want. If you just look at cosine of 2x, I'll leave it to you as an exercise, but you can work it out carefully. Do the substitution u is equal to 2x, and just looking at the cosine of 2x, and you'll end up getting 1/2 sine of 2x. That's a substitution integration problem, and you can do it. It's a straightforward substitution. Just try u equals 2x and it will work. And you'll end up getting 1/2 sine of 2x. And you can just check it in reverse now that I've given it to you, right? If you differentiate sine of 2x, you're going to get 2 times cosine of 2x, and the 2 will cancel with the 1/2, and you'll just be left with cos of 2x. So that's the antiderivative of cosine of 2x. Now for sine of x, we can just go plus cosine of x, because if I differentiate cosine of x, I get negative sine. So this will work just fine as an antiderivative, and now we can plug in our endpoints, pi over 6 and 0. Okay, now let's go ahead and do that. So what we're going to get, I'll just put this over here so we have space. So if I plug in pi over 6, I'll get 1/2 times sine of pi over 3. Right? If I plug in pi over 6 for x here, I'll get 1/2 sine of 2 times pi over 6. 2 times pi over 6 is pi over 3. So that's where that came from. And then we have plus cos of pi over 6. And then that's the first set of brackets. That's what you get if you plug pi over 6 into this whole expression. Now we'll take 0 and plug it into the whole expression. We'll have minus 1/2 sine of 2 times 0 is just 0, so it'll be sine of 0 plus cosine of 0. And that's what you end up getting. Okay, let's work out each piece on its own. Sine of pi over 3, that's actually the square root of 3 over 2. Use your trig table, special triangles, whatever you prefer, but that's how you can get that value. Cosine of pi over 6 is also root 3 over 2. Here we have 1/2 sine of 0. Sine of 0 is just 0, so that's going to be easy. That'll just disappear. And then cosine of 0 is equal to 1. So what you end up having here, this will be 1/2 times root 3 over 2. So 1/2 times root 3 over 2, that's actually going to be root 3 over 4. Then we have plus root 3 over 2. And then minus 0 plus 1, so minus 1. And really, what this amounts to is if I combine these, I can get a common denominator here. Write this one as 2 root 3 over 4. Right? Multiply this on top and the bottom by 2, and you'll get 2 root 3 over 4. And if I add it to root 3 over 4 here, I'll have 3 root 3 over 4, and then the minus 1 is still there. Let's leave it as that. That's our final answer for computing A1. So I'll just put a box around that value so it's easier to spot later when we're looking back over work. That's an important value. That's what we get for A1. So back to what we were doing here. Our total area that we're trying to find is given by A1 plus A2. We just need to find A2 now. So we'll do the same thing. We're just going to work this one out in the exact same manner. And it's not really any harder. It's the same thing. So we can get a chance to practice this technique again. So A2 is the definite integral from pi over 6 to pi over 2 of, well, the absolute value of sine of x minus cos of 2x. Right? And really, it's the same question that we're going to ask. That same thing we did up here. Right? When we were working out this one, we needed to get rid of those absolute value signs. That's the first thing you need to do. Are these absolute value signs doing nothing, in which case the sine of x would be the upper function, or are they changing the sign of what's inside? Are they actually changing the order of subtraction like they did in A1, right? In this case, what they did, since cos of 2x was actually the larger of the two functions on the interval 0 to pi over 6, and we checked that down here by using a single test point, we use it 0 as the test point, it turned out that actually those absolute value signs had the effect of changing the order of subtraction. Now, what's going to happen down here? Either the same thing, maybe it'll do it again. Maybe the cosine of 2x is actually the bigger function here as well, or maybe sine of x is the bigger function. If sine of x is the bigger function, well, then that means those absolute value signs do nothing and we can discard them. But if cosine of 2x ends up being the bigger function like it was in the other case, in the previous calculation up here, then in that case, those absolute value signs are going to have the effect of changing the order of subtraction. So we need to check. And again, we're going to do that by just picking some point between pi over 6 and pi over 2. You have the freedom to choose any point in that interval with the exception of pi over 6, because pi over 6 happens to be the point where sine of x and cosine of 2x are equal. So that won't give you any information. So pick any other point. You can pick pi over 4, pi over 3, or pi over 2 is the one I like to use here just because it works out nicer, it's easier to test. So pi over 2 works. And again, why is it that I'm allowed to choose this endpoint but not this endpoint? And the reason is because this endpoint, pi over 6, was exactly the solution to this original equation that we were considering. That's the point at which sine of x and cosine of 2x agree. So that's why pi over 6 cannot be used as a test point. But pi over 2 can. So let's do that. Sine of pi over 2, well, that's going to be equal to 1. If I plug it into cos of 2x, I'm going to have cos of 2 times pi over 2. Well, it's just cos of pi. And cos of pi is equal to -1. So that means sine of x is greater than cos of 2x when x is equal to pi over 2, and hence it's the upper function for this entire region. So what we're going to do is actually just throw those absolute value signs away. They don't do anything. So we can write this as the definite integral from pi over 6 to pi over 2 of sine of x minus cosine of 2x. So now we've dealt with the absolute value signs. They're out of the way, and we can go ahead and finish this off. So what we'll do is first we got to find an antiderivative, right? We're going to want the antiderivative of, we'll start with sine of x. Antiderivative for sine of x, that'll be negative cosine of x. And then an antiderivative for cosine of 2x, well, we already worked it out. We can, in the previous example up here, 1/2 sine of 2x, right? I mentioned that you can do that with a substitution. It's the same thing here. You can carefully work that out with a substitution. Take the substitution, u is equal to 2x. So we have subtraction in between, so we'll have minus 1/2 sine of 2x. And that'll be evaluated at our usual bounds, pi over 6 to pi over 2. Okay, and now we'll go ahead and plug those in. So we'll do that carefully. We'll take our time. Let's plug in pi over 2 first, and I'll go back over here so I have lots of room. So if I plug in pi over 2, I'm going to have negative cos of pi over 2 minus 1/2 sine. And if I plug pi over 2 in for x here, I'm going to have 2 times pi over 2 is actually just going to be pi. So I've got minus 1/2 sine of pi. So that's the first pair of brackets. Then minus whatever you get for this expression when you plug in pi over 6. So we'll have minus cos of pi over 6 minus 1/2, well, sine of 2 times pi over 6, which is pi over 3. Right, if I take negatives, or pardon me, take pi over 6, plug it in for x, when it gets multiplied by the 2, it's going to become pi over 3. So that's what we get, and now we just need to work everything out. So let's do each as much as we can in small chunks first. So cos of pi over 2, that's equal to 0. Sine of pi, fortunately, is also equal to 0. So this whole pair of brackets, this whole first pair of brackets disappears. That's handy. And then here, what are we going to have? We'll have cosine of pi over 6. That's equal to root 3 over 2. And then we have sine of pi over 3, which is also equal to root 3 over 2. So we put everything together now. We can finish this off. What's going to happen? This negative is going to cancel with that negative. If you distribute this negative into the brackets, it's going to cancel both of these negative signs, and you just have plus root 3 over 2 plus 1/2 root 3 over 2. So we'll have that here. We'll have root 3 over 2 plus 1/2 root 3 over 2. 1/2 times root 3 over 2 is just going to turn into root 3 over 4. So plus root 3 over 4. And then if you can get a common denominator there, and you can combine those into a single fraction, you'll get 3 root 3 over 4. And that is what we get for A2. So now, to get our final area, we've got A1 worked out here, and we've got A2 worked out here. We'll just add those together, and we'll get our final answer. So hence, we can say, therefore, the area is given by the sum of A1 and A2, which is 3 root 3 over 4 minus 1. That was our A1. And then A2 was down here, 3 root 3 over 4, so plus 3 root 3 over 4. And what do we get? If we combine these, we'll have, if I got 3 root 3 over 4 plus 3 root 3 over 4, that's going to be actually 6 root 3 over 4, and then we still have minus 1. So then our final answer, if I can reduce the 6 and the 4 by a factor of 2, right? So I'll have 3 root 3 over 2 minus 1, and that is our area. That's the area bounded between the graphs of y equals sine of x and y equals cosine of 2x, between the boundaries x equals 0 and x equals pi over 2. So that's our final answer.